The arrangement of common form of modern periodic table can ultimately be linked to electronic configuration of atoms of elements. And one should be familiar with atomic orbitals and electronic configuration to fully understand this arrangement. In the context of electronic configuration, it is discussed what atomic orbitals are and how electrons of an atom are distributed among its atomic orbitals. Or in other words, what electronic configuration of an atom is and how it is found. In such discussions, it is stated that the general order by which atomic subshells are filled or occupied by electrons is as follows. First, the 1s subshell is filled, then 2s, then 2p, then 3s, then 3p, then 4s, then 3d, then 4p, and so on up to the 7p subshell. In fact, this order of filling is a reflection of order of energy levels of atomic subshells, since based on AFBA or building up principle, orbitals are filled in the order of increasing energy levels, or in other words, orbitals with lower energy levels are filled before the ones with higher energy levels. For example, if the 1s atomic orbital is filled before the 2s atomic orbital, it is a result of lower energy level of the 1s atomic orbital in comparison to that of the 2s atomic orbital. It is also good to mention that the general order of energy levels of atomic orbitals in neutral atoms obeys the N plus L rule, also known as other names like the Madelung rule, the Janet rule, and the Kleczkowski rule. Based on the N plus L rule, where N is the principal quantum number and L is the azimuthal quantum number, subshells with lower N plus L values are filled before those with higher N plus L values. And for subshells with equal N plus L values, the filling of the one with a lower N value precedes the filling of the one with a higher N value. In this regard, we should also pay attention to capacity of atomic subshells, or the number of electrons required to completely fill each kind of atomic subshell. In electronic configuration of atoms in their most stable form or ground state, among many other possible atomic subshells, only 4 types of atomic subshells are observed to be filled, which are s, p, d, and f atomic subshells. Based on number of orbitals of each atomic subshell and the fact that each orbital, in accordance with the Pauli exclusion principle, can contain at most 2 electrons, capacities of s, p, d, and f subshells are respectively 2, 6, 10, and 14 electrons. This means when we build up electronic configuration of atoms by increasing atomic number one by one, or in other words, when we consider all 118 approved elements in a step-by-step sequence, in which we move from the element with atomic number z to the element with atomic number z plus 1 in each step, the complete filling of each S subshell is associated with 2 elements. The complete filling of each P subshell is associated with 6 elements. The complete filling of each D subshell is associated with 10 elements. And the complete filling of each F subshell is associated with 14 elements. Based on such discussions, it is easier to guess or understand the outcome. At first, the 1s subshell is filled, where its filling is associated with two elements, hydrogen and helium, with atomic numbers 1 and 2 respectively. Then the 2s subshell is filled, where its filling is associated with two elements, lithium and beryllium, with atomic numbers 3 and 4 respectively. After that, the 2p subshell is filled, where its filling is associated with six elements, boron, carbon, nitrogen, oxygen, fluorine, and neon, with atomic numbers from 5 to 10. Then we have the filling of 3s subshell associated with two elements, sodium and magnesium, with atomic numbers 11 and 12 respectively. Subsequently, the filling of 3p subshell happens associated with six elements, aluminium, silicon, phosphorus, sulfur, chlorine, and argon, with atomic numbers from 15 to 18. Afterwards, the filling of 4s subshell occurs associated with two elements, potassium and calcium, with atomic numbers 19 and 20 respectively. It is followed by the filling of 3d subshell associated with 10 elements, scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, and zinc, with atomic numbers from 21 to 30. Then we have the filling of the 4p subshell associated with six elements, gallium, germanium, arsenic, selenium, bromine, and krypton, with atomic numbers from 31 to 36. This continues by two elements for the 5s subshell, 10 elements for the 4d subshell, 6 elements for the 5p subshell, 2 elements for the 6s subshell, 14 elements for the 4f subshell, 10 elements for the 5d subshell, 6 elements for the 6p subshell, 2 elements for the 7s subshell, 14 elements for the 5f subshell, 10 elements for the 6d subshell, and finally 6 elements for the 7p subshell, covering all 118 approved chemical elements, where it is important to note that in some cases, ground state electronic configuration of atoms don't obey this general trend in an exact manner. By having one or two electrons moved from an expected atomic subshell to another one with a close energy level. Here, another important point to remind is that the horizontal rows of the periodic table are called periods, and the common form of the periodic table consists of 7 complete periods. The first period, or the period 1, containing only 2 elements. The second period, or the period 2, containing 8 elements. The third period, or the period 3, containing 8 elements. The fourth period, or the period 4, containing 18 elements. The fifth period, or the period 5, containing 18 elements. The sixth period, or the period 6, containing 32 elements. The seventh period, or the period 7, containing 32 elements, where atomic number increases from left to right in each period and from top to bottom across periods. It is also important to note that the two rows at the bottom of the common periodic table in fact belong to locations after barium and radium in 6th and 7th periods as their original places. However, since their inclusions in 6th and 7th periods will give us the 32-column format of the periodic table, which is very long and hard to represent, it is preferred that these two rows, commonly known as lanthanoids and actinoids, are represented separately at the bottom, with consideration that there are parts of periods 6 and 7 and not different periods in their own. Having such information in mind, we can come back to the question: how is the periodic table arranged according to the electronic configuration of atoms of elements? The arrangement of the common form of the periodic table shows us that a new row or period starts whenever a new shell is added to the electronic configuration of atoms. Or in other words, when building up electronic configuration of atoms by increasing atomic number one by one, entrance of the last added electron to a new or outer shell starts a new row or period and ends the previous one. We can check this on the common form of the periodic table. At the beginning, we have the period 1 with two elements, hydrogen and helium, associated with the filling of the 1s subshell for the first time, where the 1s subshell belongs to the first shell. After that, the period 2 starts with the element lithium associated with the filling of the 2s subshell for the first time, where the 2s subshell belongs to the second shell. So when increasing atomic number one by one, the element lithium is the first element at which the second shell receives electron, and this is accompanied by end of the period 1 and start of the period 2. Similarly, the element sodium, located at the beginning of the third period, is the first element at which the third shell receives electron, and this is accompanied by end of the period 2 and start of the period 3. This pattern is also obeyed by the following periods. So generally, the period n starts at the element in which the shell n receives electron for the first time, where based on the order of filling of atomic subshells, this means that the period n starts at the element in which the ns subshell receives electron for the first time. And with the exception of the first period, the period n ends at the element in which the np subshell is completely filled for the first time. In other words, the period n is accompanied by the filling of the ns subshell and any other possible subshells with energy levels higher than the ns subshell but lower than the n plus 1s subshell. For example, the period 6 is accompanied by the filling of the 6s, 4f, 5d, and 6p subshells. Based on such discussions, we see how the arrangement of the common form of the periodic table is linked to the electronic configuration of atoms of elements. In this regard, it is good to pay attention to some other facts too. One of notable characteristics of the periodic table is its blocks. The arrangement of the periodic table based on the electronic configuration of atoms leads to formation of 4 s, p, d, and f blocks associated with the filling of s, p, d, and f subshells respectively. There are collective names associated with these blocks. In general terms, the elements of the S and P blocks are called the main group or representative elements. The elements of the D block are called transition elements or transition metals. And elements of the F block are called inner transition elements or inner transition metals. This grouping of elements into different blocks is a valuable tool in analyzing chemistry of elements since the basis of this grouping, types of atomic subshells under filling, plays an important role in determination of chemistry of elements, and no wonder it is a common practice to analyze chemistry of blocks separately by discussing chemistry of main group, transition, and inner transition elements distinctly. Although just in general terms, since similarities in properties of some elements from different blocks don't allow consideration of clear boundaries. Also, it is important to note that based on the electronic configuration and capacity of atomic subshells, each row of the block F should contain 14 and not 15 elements. And in fact, one element from each row of the current F block, which has 15 elements in each row, belongs to the block D, where there is debate on choosing either the element at the beginning of each row or the element at the end of it as the D block element. And currently, due to similarities of properties, 15 elements of each row are considered together. In other words, from the first row of the current F block or lanthanoids, either lanthanum or lutetium, and from the second row of the F block or actinoids, either actinium or lawrencium should be moved to the block D as group 3 elements of periods 6 and 7. But due to associated debates, this has not been done yet. We discussed how the arrangement of the periodic table is based on the electronic configuration of atoms. There is another important aspect of the arrangement of the periodic table, which is similarities in properties of some groups of elements. Vertical columns of the periodic table are called groups, also known as families, where there are 18 groups numbered from 1 to 18 based on their position from the left side of the periodic table. In general terms, elements of a same group share similar properties different from properties of elements of other groups. Although similarities in properties of nearby elements of a same period can also be considerable, as in the case of the D block elements or more profoundly the F block elements. Indeed, historically, observation of such similarities in properties of some groups of elements led to proposal of the periodic table. The first recognizable periodic table has been attributed to the Russian chemist Dmitry Mendeleev, who published his first periodic table in 1869 and a second improved version in 1871, where many other great scientists had also made great contributions to the concept of the periodic table before or after him. Mendeleev and scientists of his era were unaware of electronic configuration or even atomic number, but they were keen to notice similarities in properties of groups of elements. And based on that, they were able to give rise to initial periodic tables. This prompts a big question in mind. If similarities in properties of some groups of elements led to arrangement of elements in the form of a table called the periodic table, why did we discuss the arrangement of the periodic table based on the electronic configuration of atoms? The answer lies in the close relationship between electronic configuration of atoms and properties of elements. Any similarities or differences in properties of elements can ultimately be linked to their electronic configuration, and the recurring pattern in the electronic configuration of elements when listed in the order of increasing atomic number is the cause of recurring pattern or periodicity of properties of elements that leads to formation of groups of elements with similar properties. So we can conclude that the underlying basis of the arrangement of the periodic table and any associated behavior is the electronic configuration of atoms and its associated recurring pattern. Finally, it should be noted that based on the electronic configuration of atoms, there are many other proposed formats for the periodic table. The one represented here, which can be considered as the common or standard form of the periodic table, is based on IUPAC periodic table of elements dated the 1st of December 2018. For the original IUPAC periodic table of the elements and also for notes and updates to it, visit www.iupac.org.